Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In this video we continue talking about spatial data structures, and we're going to continue some of the code we started last time and looking at brute force attempts to find neighbors. So we talked about how our goal is to be able to pick a point and a radius around it and find all of the neighbors that are within that radius. And that the brute force approach to this was to run through all the other points and see which ones were within that distance. So we created this trait called neighbor finder because it is going to, because it's going to be helpful in all of the things that do this. I'm going to want to define a distance function, and the distance function will take 2 points, both of type A, because A is the type that we're working on here, and it's supposed to return a double. We'll come back and we'll fill this in just a second, but the code I want to write right now is the brute force neighbor finder. So we'll create a new Scala class, the brute force neighbor finder, and our brute force neighbor finder works on A and extends a neighbor finder of A. And of course this has an error right now because it doesn't implement this method. Let's go ahead and say that this returns unit. Now this method is perfectly happy because we've written the method. Of course, it doesn't do what we want yet. So the idea here is that we're just supposed to run through all of the points that are in here and find the neighbors. Well, we need some points first. And this should be a sequence. In fact, I need it to be an indexed sequence of type A. I really don't care if exactly what type of sequence it is, as long as I can get to the values quickly. Maybe we'll modify that in a bit when we try to write some test code for this. So we get a whole bunch of points, and I want to find out which ones are close enough to a particular point that's passed in, and for all of those that are, check to see, call this visit method on them. So let's do for A, or for P in points, this would be as simple as if the, actually I should not call that method dist and the thing that I'm passing in here, how about we call this search dist. And just to be consistent, though you don't have to do this, so that it matches across the different implementations, I'll do that. If dist of P, comma, P and T is less than or equal to search dist visit P. And that's a perfectly happy brute force method. It's order in. It runs through all of the points. And of course, if we called this on all the points, we would wind up going through order in squared operations. Now, this calls this method dist here, which we haven't written yet, and that's a bit of a problem for us. So how do we calculate the distance? So one of the things is, in our drawing, we had all of our data is in 2D. Okay, so they have an x coordinate and a y coordinate. But in reality, I don't want to limit myself to that. I want to have the ability to have multiple dimensions, however many I want. And so to calculate a distance on that, well, the Cartesian distance is equal to the sum of the squares of the distances, and I take the square root of that. So I would want math dot, oops, with an m, math dot square root of, I want to take the sums of the differences, so this would be P1 sub 0 minus P2 sub 0 quantity squared times P1 sub 0 oops, like that, minus p2 sub 0 plus, and then I need the same thing, whoops, the plus should go here, I would need the same thing for p3, p4, or, well, you'll notice even this right here is an error of what if this were dot x and dot x dot x dot x. Well, if I did dot x dot y dot z, that's great for up to 3 dimensions, but I start running into problems beyond that. The other approach of doing this with indices scales much better to an arbitrary number of dimensions, but my type A has to be something that I can index, and that's the problem right here, is that it says you can't index this. So what does this mean? Well, really what this is doing is it's calling the apply method. It's saying that this needs to be a function, and the function is taking a single argument of type int, and it returns, well, hopefully a double. And that's the type that we're going to work in here. So I want to put some restrictions on my type A. I want my type A to be anything that is a subtype of int to double. And in fact, it turns out I don't actually care if it's a direct subtype. I care if it is anything that is implicitly convertible to a subtype there. And that's the fact that I made this trait is not going to be happy with that. Actually, I'm going to just change this to a class for that reason so that we don't have to deal with that problem right now. Okay, so now this doesn't like the fact that I'm doing that, so I have to do the same thing here. Okay. Abstract class. Okay, all my errors went away, only because I have a 0 here. But this needs to be added to the sum of the squares, or to the square of the difference of the next term, and the next term, and the next term. And I don't necessarily know how many of those there are at this point. Maybe it would be nice to pass that in. So let's see, where do I want to pass this in? Yeah, I think I'm actually going to pass it in here. Let's eval dim is an int, so that all neighbor finders will have a dimensionality to them. That is actually going to force us to pass it in here, and then we'll pass that through to the neighbor finder, and we need to come up with something happier here. So I need to take the sum of the squares of the differences, which different ways for me to do this. How about we do let's do a P1, P2 dot zipped, except I can't do zipped because they aren't specifically sequences, they are just functions on things. Okay, 0 until dim dot map to map of I sub P1 of I minus P2 of I, and then I want to square those values, and then trying to think, because so the problem is if I do this, and then take the math dot square root of that, that compiles. It's inefficient, and since we'd be doing this by adding a view, I can make this so that it is non-strict, and these things kind of happen. This is good enough for right now. By adding the view, I make it so that the map doesn't actually create a completely new array or whatever we have. But okay, we'll live with this. So I take the sum over all of the squares of the differences from 0 up to the dimension, and I take the square root of that, and that gives me a distance. Okay, so we've gone through, we've written something that is a reasonably functional brute force neighbor finder. We haven't tested it. It implements our neighbor finder, and we added some code in here. We realized what bounds we need to put on the type here, and this is a nice flexible bounds on the type. And that's it for this video. We'll come back in the next video and we'll start talking about how we can make this more efficient, what we can do that is better than brute forcing through all of these. Something so that if our number of points was much, much larger than 100, say 1 million, 10 million, 100 million, so we'd actually be able to do it. Something where order n squared is not happy.